Hi, good evening to one and all. I welcome you for my video lecture, my first video lecture, analysis and design of flexural member by working stress method. So this is the method of one of the method to design the beam. We have two type of methods. One is working stress method and limit state method. Probably the limit state method is has been used very high nowadays. Not the working stress method is not preferably good for designing of a singly reinforced or doubly reinforced beam. And this is an olden part of the method. Anyway, we will see the failures which occurs in beam due to working stress method and the codal provisions in the working stress method, which is available in IS 456, and the procedure for designing a flexural member by working stress method. So this is the three topics we are going to see. So one is the kind of member failure, and second is we are going to see codal provisions. At last, we are going to see the design procedure for working stress method of a flexural member. Okay, so here we may able to see the analysis of beam in working stress method. So in this, let us have this is in a uh, beam which is in a reinforced and which is as a two zone. Already we know that each has a two zone. One is this zone is a tension zone and this one is a compression zone, and this line is called as a neutral axis line. So this tension zone we provide the steel which is nothing but they call it as a singly reinforced section, and the reinforcement which is here, which is here, the reinforcement which is here is tension, and the upper part we provide which is compression reinforcement. Okay, and the reinforcement is one side it is provided which is called as a singly reinforced beam, and the both the side of tension and also compression if you have provided, we may call it as doubly reinforced beam. So here we may see the three different figures. So one is called as a balanced section, and another one is called as under reinforced section, and the third is called as over reinforced section. So let us know about the figure first. So already this is a beam structure, right? And which has top of compression zone and bottom of tension zone, and the reinforcement is provided in the tension. So this is the normal stress distribution diagram, and which may be able to see that called as sigma CBC and sigma ST. So right, in this section is called as balance section. This balance section is failures occurs simultaneously, as we know that the neutral axis is center and which will be traveling parallelly. The compression zone and the tension zone will traveling parallelly, and this is called as NC is equal to N. That is actual neutral axis is equal to critical neutral axis. N is the actual neutral axis. The actual neutral axis, which is in the center of this point, the 0 point, that is neutral axis point, the basement up is nothing but of actual neutral axis. And critical neutral axis is NC, which is the both or in same point. And under reinforcement section, NC is greater than N. Yeah, NC is, wait a minute. Yeah, NC is greater than N, and in over reinforced section, NC is less than N is greater than NC. That is, N is here is the actual neutral axis, and NC is a critical neutral axis. So the failures occurs in the balance section, that is this one, which occurs simultaneously, and in the over under reinforced section, which occurs first in steel and next to the concrete. And the third structure, which failures occurs in first in concrete and to the steel. So for the balance section, we may use the formula called moment of resistance, tension or compression. And for under reinforced, we use only tension formula to find moment of resistance. And in over reinforced section, we use a moment of resistance in compression formula we use here. So we may able to identify, we have three sections here. One is balance section, under reinforced section, and over reinforced section. So we may be able to easily view in the short note NC is equal to N. Here you may see NC is greater than N, and here you may see NC is less than, that is N is greater than NC. So this is the three part of sections. And next. So here in the annexure B, IS 446, the structural designing, the working stress method, the assumptions of working stress method can be seen, and permissible stresses in concrete sigma CBC from table 21, page number 81. So here we may able to see a few codal provisions which has been given in IS 456 for working stress method of singly reinforced. So assumptions, permissible stresses in concrete, which is in table 21, page number 81. Permissible shear stress in concrete, tau Z, that is page number 23, page number 84, and maximum shear stress in concrete, that is tau max, table 24, page number 85. Permissible stresses in steel, that is sigma ST, table 22, page number 82. And B3, which is permissible load in compression member, and maximum subjected to combined axial load and bending, that is B4, and B5 is a shear. So here probably we may use the permissible shear stresses and a shear here. So this both we will use at the maximum. So this is some of the few formulas which is we are going to apply in this design and analysis of singly reinforced beam by working stress method. So this is as you've seen in the before previous slide. So this is a working stress method. The analysis of beam can be done by these following equations. So for analysis of for analysis we may able to understand the required data will be moment of resistance in tension and compression. So you may see this is moment of resistance in tension and moment of resistance in compression, the formula. So for this we need an actual neutral axis and critical neutral axis. So this is the formula to find actual neutral axis, and this is the formula to find the critical neutral axis. And JKQ values, and this is the constants of design constants values. This can be found through the based on this formula. So as we discussed, the balanced reinforcement section, if you get a balanced reinforcement section, that is NC is equal to N, we may use compression or tension formula. So over here, which is tension and compression, any one of the formula can be used. And as it is in under reinforcement section, we may use a tension formula, which is a tension formula, which is upper hand. Okay, this is tension formula. At last over reinforcement section also, we may use compression formula, which is here down compression formula. To analyze the resistance of beam, that is maximum moment of resistance can be identified by the based on these formulas. Next. So this is the part of analysis. So this part of analysis, we may have to identify the moment of resistance, load, the maximum load that can be identified this from this working stress method of resistance. And next, the design steps of beams in working stress method. So here we may see the steps which is involved in working stress method for design of singly reinforced. So not only singly reinforced beam, it may be reinforced kind of in a beam. First of all, we would like to identify the dimensions of the beam, effective span of the beam, and load calculation, and bending moment and shear force of the beam, and maximum depth is required. So in this point is very, very important. That is minimum depth requirement is very, very important. So actually from here, we will be finding the maximum adaptation of the depth, which is safe or unsafe, and which is minimally provided or not. So once the depth providing depth is not up to the equivalent mark, we may have to change our design to the again to the first step and come back to here. So here we will check the minimum depth requirement. Okay, the minimum depth requirement should satisfy the conditions. So otherwise we have to go back to the dimensions and we have to change the dimensions to satisfy these conditions. And next is area of tension reinforcement and shear reinforcement, part loss, and final detailing drawing. Step one. So this might be a given data for the students, or given load, span of the beam, load of the beam, and grade of the materials. And the step one, the constants can be identified. That is KJQ can be identified. So you have the formula for KJQ. and this is the design constants. And the next step, design of beam. So beam, dimension of the beam. So the dimension which involves depth and overall depth, effective cover, and the breadth, and the effective depth. So depth of the beam can be identified by this condition. Depth is equal to span by 10 to span by 8. The ratio, whatever it can be taken. So the overall depth is D plus effective cover. Effective cover can be taken from 25 mm to 50 mm. This is the range, and anything you can take it at. And breadth of the beam. So breadth of the beam is from the ratio of D by 2 to 2 by third of D. From this ratio, we can identify, right, and effective span. So for the effective span of the beam, we have two conditions. One is center to center support, clear span plus effective depth. So in this both the condition, whichever is least, we may take it that. In the load calculation, we may see we have self weight of beam, BD, unit weight of BD into unit weight of concrete. So the unit weight of concrete for plain concrete is 24 kilonewton per meter cube, and reinforced concrete 25 kilonewton per meter cube. So the total load will be dead load and live load, self weight plus float finish. So this is the load. This will be the load calculation for this method. And the next step is belong to bending moment and shear force. So the bending moment and shear force can be calculated based on the condition it is specifically asked for you. One is for simply supported beam, the moment is WL squared by 8. For cantilever beam at a support, it's WL squared by 2. And for fixed beam at center, that is load is at the center. Okay, WL squared by 24. So shear force, and for simply supported is WL by 2. Cantilever is W into L, and fixed is WL by 2. This already we have known. This is the standard formulas which has been given for the varying in conditions. So after identifying this, the area of tension reinforcement and the area of shear reinforcement has to be concluded. And once this has been identified, and the total design is over. So this is, and the final detailing drawing can be done. So this is the steps involved in beam of working stress method. And these are the various steps which is get of involved. And thank you all for watching this video. And with this, we'll conclude here with the steps of beam. Thank you for watching. Thank you all.